Alright, so this video is going to be on separable differential equations. First of all, um, what is a separable differential equation? So a separable differential equation is a differential equation that can be written as dy dx equals to, let's say, some function of x, let's call it gx, times some function, let's say, of y, let's call it hy. It's not the case that all differential equations can be written in this form. So in particular, notice that we are here talking about a separable first order differential equation, because what we have here is y prime equals gx times h of y. So we're dealing with a separable first order differential equation. And so let me give you an example of a differential equation that is not separable. So consider the following differential equations. Consider the differential equation dy dx equals, let's say, sine x plus cosine y. This is a differential equation which is a first order, and if you notice over here, I am not able to express this as a product of a function of x and a function of y. I mean, this is here sine x and this is cosine y, and obviously I am not presented here with a product, rather a sum of two functions. But let's look at this differential equation here. Let's say dy dx is equal to, let's say, x squared times, let's say, y, and then I'm going to say e to the sine x plus cosine of y. Okay, so here we have a situation where we have e, which is a function of sine x and cosine y, and we have here terms involving we have rather a term involving both x squared and y, and we want to see if this is a separable differential equation. Well, let me actually remind you that this expression e to the sine x plus cosine y can be written as, so let me actually take this over here and just remind you that using rules of exponentiation, I can write this as e to the sine x, okay, times e to the cosine y. So that this whole thing here becomes then x squared times e to the sine x times y e to the cosine of y. So now that we have actually written it in this fashion, you can readily see then that this here is a separable differential equation, because this is a function of x, g of x, and this is a function here of y that we're going to call h of y using our conventional notation. Now, the reason why people like first order separable differential equations is because they are very, very easily solved, generally using integration first in the variable x and then in the variable y. So suppose that you can write a differential equation in the form, let's say, d dx is equal to g of x times h of y. Then what we can do is actually, dy dx I can actually take this differential equation and I am going to multiply both sides by dx, so I get dy is equal to g x times hy times dx, and I'm going to divide both sides by hy, and what we're going to end up with is here 1 over hy, okay, times dy is equal to g of x dx. And now if I want to solve this differential equation that I began with, then it actually becomes a rather naive exercise in integration. So for example, this is going to be then, in order to find, so in order to find this differential equation, what this differential equation is, I would just take the integral of both sides. So let's say we have 1 over hy dy in respect to y is equal to the integral of g of x dx. So what we're going to end up with here, once we actually successfully integrate this function, is a function of y equals to a function of x. Let's actually call it capital. Let me actually change the name here. I'm going to change this into fancy h in a way that it evokes the fundamental theorem of calculus. Okay, so I'm going to change it into fancy h equals to fancy g, right, of x, and plus let's say c1. Now remember that when you found the antiderivative of this function here, you actually obtained a c, but once you've finished finding the antiderivative of this function, this of g of x, you actually move the c from here to here, and you obtain, let's say, the c from here minus the c from there became c1. So now you have found a solution to this differential equation, and this is the idea.